kids always ask you, why's the earth round and why's the sky blue? And sometimes we spit back, curiosity killed the cat. Well, as we grow older, everything starts to look so familiar. The color will fade to brown as our bodies grow up and our minds grow down. I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day.
I think we have an exciting talk for you lined up, and I'm really excited that all of you are here this Wednesday evening to hear about it. So our speaker today is Dr. Steve Trettel, Assistant Professor of Mathematics at the University of San Francisco. Steve earned his undergraduate degree in mathematics at the University of Minnesota and his PhD in geometric topology at UC Santa Barbara. Dr. Trettel did postdoctoral work at Brown University, then returned to California, first to Stanford as assistant professor, and then to USF where he does geometry, topology, and is now writing his own textbook. Dr. Trettel is a fantastic geometric illustrator who creates mind-bending videos. Tonight, I suspect we'll see some of those videos portraying the bending of space and our minds. We're pleased to introduce space and mind bender, Dr. Steve Trettel.
All right, well, thank you so much, Tomi, for the introduction. Thank you to Eric for all of the organizational events here. And of course, thank you to Tucker and Wonderfest for running all these wonderful events that you've invited me to. Thank you so much. I'm very excited to be here tonight to tell you a little bit about my favorite parts of math, which are geometry showing up in unexpected places. I'm a geometer by training. Like, I study geometry, like as a theoretical mathematician studies math. But I'm most excited when I find geometry outside of the field of geometry. When I'm walking around in a different area of mathematics, physics, somewhere, and geometry pops up and it surprises me. That's my favorite. I think the biggest surprise that we've ever gotten in this area is that gravity is geometry. Like, that sentence barely makes sense to me the first time I heard it. Actually, it didn't make sense to me at all the first time I heard it. And so my goal is to progress during this talk from that sentence doesn't make any sense to, whoa, I can see that's a mind-blowing idea that I probably need to learn more about. That's where we're going. Thanks everyone for coming. I'm super excited to see all the young people in the audience here. All the kids. How many of you have heard of black holes? Nice. How many of you want to hear more about black holes? Oh, you are in the right place. This is a good spot to be in the evening. This picture here is a black hole. I'm not explaining anything about it yet, but we're going to explain this whole picture throughout the talk. We're going to understand exactly what the little clear bubble is, what the big black sphere is, and what the wiggly lines are. And then we're going to use that to understand what black holes look like. So that's our goal. That's where we're going. But to start, we got to do some geometry. So geometry is like, I don't know, pretty big deal. It's been around for a long time. Here's three guys that did a lot of geometry back in the day, like 2,500 years ago. We got Pythagoras coming onto the scene and studying triangles. And like 2,300 years ago, we got Euclid and his soon following buddy Archimedes, who, for some of my students are here from geometry. I'm like Archimedes' biggest fanboy. I talk about him like every day. So you get to hear about him more today. And the mathematics that came out of ancient Greek really essentially finished the geometry of the plane. This long ago, people totally understood lines, triangles, circles, cylinders, spheres, cones, rectangles, and so on. Not to say there wasn't more math to do. Tons of mathematics over the last 2,000 years grew out of the Greeks' understanding. The things that we currently know as calculus, linear algebra, advanced geometry, high-dimensional statistics, all of this stuff lies within the purview of the Greeks. It all comes from this ancient mathematical tradition. But a really exciting thing happened 200 years ago, which is something that kind of seems obvious in retrospect. It's that we need more than that geometry to understand the real world. Here's a picture of some of the beautiful landscape around us. And that does not look like the plane. Like if you're studying perfectly flat planes, you do good at understanding floors and chalkboards, but you might not do so good at understanding the Marin headlands because the ground does not look like a plane. So we need geometry beyond the geometry of a plane. Euclidean geometry was almost so successful that it took us a long time to realize the necessity for this other type of geometry, the geometry of curved surfaces. We were doing such a good job making so many mind-blowing discoveries that this work was really formalized by Gauss in the early 1800s, like 1820s or so, working with the German government on surveying and trying to understand topography in reality. But right around the same time, a huge advance was going on in mathematics itself, with Bolyai and Lobachevsky both discovering an abstract space different from the Euclidean plane. That really showed that not only for the real world do we need to think beyond the Greeks, but also just to do pure mathematics. Even when everything's as nice as can be and as symmetric as possible, the plane isn't enough. Three-dimensional flat space isn't enough. There are abstract curved spaces out there. Again, I don't expect any of you to have heard of any of these spaces yet because, unfortunately, mathematics takes a really long time to percolate down from the research level to the public level. These spaces were discovered, it's actually the 200th anniversary. 1823 is when hyperbolic space was discovered by Bolyai. And yeah, so I want to share, we'll see some pictures of this space coming up here. But since then, mathematics has, the abstract math of curved space has really transformed a lot of the world. It's used in architecture. It's used in clothing design. It's used in theoretical physics all over the place. And one of those applications to physics, my favorite surprise peekaboo geometry in the middle of nowhere, is the theory of gravity. So the work of Bernhard Riemann, who was Gauss's student, led to the equations that Einstein was able to use to describe what turns out to be how our universe works. So to do any of that, to do any of this exciting math that happens beyond the plane or geometry of the Greeks, we need to seriously confront what's different. And what's different is this concept of curvature. So goal one in the talk is to explain what is curvature. We're going to need that if we want to talk about black holes. And here's a cool idea. If I have a bunch of surfaces in front of me, and I want to tell if a surface is curved or if it's not curved, we need to use geometry to measure it. Mathematicians need to build measuring devices. And circles are an excellent measuring device. What I mean by that is, if you think about the plane, oh, bummer, I put the answer up here. I was going to give you guys a quiz and ask you, what is the formula for the circumference of a circle? And I gave it to you. That's okay, it's a weeknight. I don't assign homework on weeknights. C equals 2 pi r is the formula for the circumference of a circle, right? What does that mean? That means that if you double the radius of a circle, you double its circumference. If you triple the radius of a circle, you triple its circumference. Why does it mean that? Well, because C is proportional to R. It's just a multiple of R. So if I were to draw a graph of the function circumference on the y-axis, radius on the x-axis, that would look like a line. What's the slope of that line? Okay, here's a quiz. 2 pi. 2 pi is the slope of that line. And from our perspective, that's how we're going to remember. This is how Euclidean geometry works. This is how the plane works. If you make a bigger circle, its circumference grows like a line. But what about on a hill? What if you were standing at the top of a hill or on a sphere and you drew a circle? What does it mean to draw a circle on a hill? Well, operationally, I could do it. I could just stand at the top of the hill. I could drag a string, and then I could stake the string at the top of the hill and walk around the hill, draw these circles going down the hill. They're all lines that are equal distance from the top of the hill, just like circles are the set of points that are the same distance from their center. But what's going on with their circumferences? Their radius is bent along the side of the hill. You have to walk a long way down the hill to get to the bottom, even though the circle's not very big at the bottom. So circumference as a function of radius grows slower than linear. Actually, if your hill was the top of a sphere, like a perfect sphere, it would be c equals 2 pi times the sine of r. But it doesn't actually matter the function. It's just that c as a function of r looks like a little bump instead of a straight line. But what about if you had a surface that looks like this? That's a little bendy in one direction and bends the other way in the other direction, like a horse's saddle or a Pringle chip, or a piece of a sea slug, or a piece of kale. What happens if you drew circles on that? Well, now the circles are bending up in one direction and bending down in the other direction, and the circles are actually longer than they would have been on the flat plane. The function circumference as a function of radius grows faster than a line. And this is how we measure the curvature of a shape in mathematics. We say your curvature is 0 if circumference grows proportional to radius. Nice straight line. We say your positive curvature if circles grow slower, and you are negative curvature if circles grow faster. And if you want a precise formula, spoiler alert for my students, this is tomorrow's lecture. We're going to derive, this is the formula you use to compute that number. You can take 2 pi r, which is the flat plane formula, minus the circumference, and you have to divide it by something. It turns out it's pi r cubed to make sure it works. It's kind of like a derivative, but it's like a fancy derivative. And that's curvature. It's like the derivative of how fast circles grow. And so mathematicians love shapes like that where it's easy to understand the curvature, but in the real world, things are kind of complicated. I've drawn a kind of wiggly donut here, and I've colored the donut. So the red points have positive curvature. That means near the red points, the donut looks like a hill. And I've colored the donut so that the blue points have negative curvature. That means anywhere the donut's blue colored, it kind of looks like a Pringle chip. And green is spots where it works like the flat plane, where circumference to radius looks linear. So a general shape is all wobbly and hard to understand, has positive and negative, and there's a lot going on. So what do mathematicians do in a case like this? We say, that's scary. Let's try and understand the simple cases first, and then put our intuition back together. So we're going to back away from this scary town. We'll come back to this scary world when we get back to reality and black holes and stuff. But let's go on a journey of constant curvature spaces, spaces where they're not curved different at every point. So a sphere, like a soccer ball, is a good positive curvature space. Bathroom wall, tiles with squares, that's a good zero curvature space. And there's a piece of coral that does a good job of being negatively curved. Of course, the mathematical idealizations, we can build examples of this in 3D as well. So a three-dimensional space with zero curvature is just the space around us, space you could fill with cubes, stacking up cubes like normal flat 3 space. Positive curvature, what would it mean for space to be positively curved? This is a little weirder to picture, but a sphere had positive curvature, like a soccer ball. So we want to make like a higher dimensional soccer ball. Here's a math way to do that. Well, we can think of a sphere. You can make a sphere out of slices, right? If you sliced a sphere, you can slice it into circles. You stack all those circles on top of each other, and they make a sphere. What if instead we took a bunch of spheres and we stacked them on top of each other in the 4th dimension? That sounds confusing, but believe it or not, that's what I do in my day job. We stack spheres and build weird spaces. And this space is called the 3-sphere. We don't need to picture it right now. We're going to learn to picture it in a second. But this is a space of positive curvature. And then if you take the discovery of Bolyai and Lobachevsky, this negatively curved space, and you just spin it around in a circle, you can build a 3-dimensional version that has negative curvature everywhere. So this sort of thing really exists mathematically. All 3 of these spaces happen. And what I want to do is talk about how do we see them? How can we see these things? Like telling you that I'm stacking spheres on top of each other in the 4th dimension is probably like one of the most unhelpful things you've heard today. So let's try and do something else. these spaces that we want to understand are three-dimensional. And good news, my brain evolved in three-dimensional space. My brain is full of circuitry that does a good job of understanding a three-dimensional world via vision. So what I want to talk about is how these spaces would look if we were inside of them. And to do that, I need to talk a little bit about what does it mean to see. So if I were looking at that ball, why do I see the ball slightly downwards in front of me and nowhere else? Well, it's because lines of light that connect my eye to the ball hit my eye in that downwards direction. You can see these straight lines here. Those are the lines of light connecting me to the ball. And so I see the ball wherever straight lines go. That's our first hint on how to understand geometry, is that light travels on straight lines. And that tells us sight is a kind of geometry detector. For any experts in the room, of course, I mean time minimizing geodesics are what straight lines mean this entire talk. But light travels on straight lines. It tells us where things are by probing them with geometry, probing them with lines. So if I wanted to understand how big that ball looks, what would I do? I would do some good old-fashioned trigonometry. I would draw the ball in front of me and see how far away the ball is. How big it looks in my vision is the angle it takes up in my eye. I could compute that angle with some trig. And that expression looks nasty, so I'd probably simplify it a little bit. And I'd find out that the size of a ball in my vision is approximately twice its radius divided by the distance away from me. This is all just with like geometry. What does that mean? That means that if I take an object and I put it twice as far away, it looks half as big. Which that makes sense, right? Like I'm looking at these people in the back of the room there. It's not like you're actually 1 inch tall. Like you're definitely bigger than my thumb. But from my perspective, you look the same size as my thumb. That's because twice your height divided by the distance is equal to twice the radius of my thumb divided by the distance. The other thing we can see is when you look at a sphere, the lines of light from your eye to the sphere are kind of making a cone. Like they're connecting your eye at a point, and then they're hitting the sphere along this cone. And that cone intersects the sphere, only letting you see less than half of it. If you look at a picture of the Earth from space, like this picture's from the Apollo missions, you can see the South Pole here, right? But you can't see the South Pole and the North Pole at the same time. That's probably seemed obvious to everyone. No one's ever probably thought about that. Why can't I see the North Pole and the South Pole at the same time? But the reason is geometry. It's that your lines of sight can't hit your eye and hit the North Pole and the South Pole at the same time on a sphere. You always see less than half of a sphere. If the sphere was infinitely far away in the limit, you'd see exactly half, but never ever more. You always see less. And these are the sort of facts we can figure out with high school type geometry. But what I want to do is replace this flat space, the space of the Greeks, with curved space and redo all of that math and think about what things would look like. So here, look at that Earth. Imagine you're looking at the Earth from space. But space is curved. What curvature does is it changes how light works. It changes what the straight lines are. When space is positively curved, straight lines bend together. They come back together. When space is negatively curved, lines move apart faster. That's the same pattern we saw with circles, right? Circles grow slow in positive curvature and fast in negative curvature. So if you were here in this top animation, what I'm doing is I'm changing the curvature of space. I have like a magical universe device where I'm turning the wheel on curvature. And your lines of sight are getting close together when space is positively curved. Now space is flat. And now space is negatively curved. Does anyone have a suggestion? What do you think the sphere looks like as I stand here turning my like mad scientist dial when I ramp the curvature up to be negative so light rays move away faster? What happens to the Earth in your vision? Does anyone have a guess? Yeah. What happens?
When it gets negatively curved, the Earth you can't see the Earth.
Yeah, when it gets negatively curved, light goes away really fast. So very little light hits the Earth. So the Earth looks really small, just like the people in the back of the room who look really small because light goes away. When space is positively curved, light comes back in and like hugs the Earth. And so more light hits the Earth and it might look a little bigger. Yeah, that's a great guess. So let's look at that a little closer. Here, imagine you lived on the surface of this sphere. Imagine you were an ant and you lived on here and light traveled on the sphere. So these yellow lines are lines of light. You live at the North Pole. That's your ant house. And you have this green ball. And I don't know why the green ball is moving around, but you want to look at the green ball. When the green ball is close to your face, all those lines of light are hitting the green ball. That makes sense. If I put a green ball in front of my face, it'd be really big. When the ball moves away, less lines of light hit the green ball. That makes sense. When something moves away, it looks smaller. But what happens when it gets more than halfway around the Earth, around the sphere? Now, all the rays of light are hitting it again, right? So how big does it look in your vision? It looks the same size as if it was close to you. The same amount of light is hitting it. Here's what we would see. This isn't a green ball, this is a chalkboard ball, but use your imaginations. As the ball moves away from you, it gets smaller and smaller until it gets to the equator, and then it gets bigger and bigger again, right? And we can do some math, we can do some trigonometry, and we can say exactly how much bigger it gets if we wanted to. This is spherical trigonometry. People have known how to do this for a long time. But this is a way to understand positively curved space. We can write down an actual formula that tells us instead of 2 pi over d, it's 2 pi over sine of d. Linear got replaced with a sine curve again. Ooh. So let's look at this a little closer. Instead of picturing a green featureless ball moving away from you, I want to picture that me and you are standing in a space of positive curvature, and I'm walking away from you. What happens? At first, when I'm right up in your face, my face looks big. Then I move away, my face looks smaller. But I keep moving away, my face looks bigger, right? Just like we saw with the green ball. It gets smaller, then it gets bigger. But we need to pay a little bit more attention. What is happening? Oh, my phone's not synced. Let me see. There we go. What's happening to this ball when it's really far away? Rays of light are moving back in. How much of that sphere are we seeing? More than half. Light rays are coming around, hitting the sphere on the back side. That's pretty cool mathematically, but practically it's really horrifying. Because think about what's going to happen. My face is going to get smaller. That makes sense. But then my face is going to get bigger. But also, you're going to see more of my face because light has wrapped around by curved space and touched the back of my head. What happens when I keep moving back? My face gets bigger, and you see even more of my face. What happens if I were at the South Pole? What happens if I were on the opposite side of the Earth than you? If you looked forward, you'd see my face. But if you looked this way, light would also go to the South Pole. You'd also see my face. My face would be everywhere. My face would actually be the whole world around you. That's horrifying. I don't want to see that. But I can't help myself. I love graphics programming, so I'm going to inflict it on all of you too. So here's a simulation of what it would look like if you were looking at this 3D model of a person and they were in positively curved space and you walked away from them at a uniform speed. You're just going to back up from them at a speed of 1 meter per second. Watch the ears. Oh no. Oh no. Oh, make it stop. And now he's at the South Pole relative to you. If you turned around, If you looked behind you now, you would see his hair. If you looked above, you'd see the top of his head. If you looked down, you'd see his feet. So be thankful we don't live in a positively curved world. But here's what an Apollo mission would look like from a positively curved world. If we were looking back at the Earth before re-entry, what would we see? The Earth would look big. That makes sense. Our face looked big. And just like we could see both of our ears on the front of our head, you can see both the North and the South Pole on the front of the Earth. So this is a good way to tell. If you ever are lucky enough to get put in a weird spaceship and shot out into space, and you realize you have no idea what space you ended up in, you wake up after your cryogenic nap and you're like, is space positively curved, negatively curved, or zero? You can just find the nearest planet and see if you can see both poles. If you can see both poles, it's positively curved. And here's just a bunch of balloons in a positively curved space, like just a bunch of balls. All these balls are the same size. But what I want you to notice is some of the balls in the back, when they move back, they get really big. That's like your face. When it's getting really far away from you, it gets really big. So parallax, telling sizes by distance and position, is really difficult in this space. Playing baseball in this world would be really, really hard. It actually turns out when you throw a ball away from you, when it starts to look bigger again, you might want to duck because it looks like a ball is coming at your face, but it's actually never going to hit you. It's as far away as it can go. So this is a positively curved world. What would happen if I took this exact world right here and I went back in my crazy spaceship with my curvature dial and I yanked the dial really irresponsibly all the way over to negative curvature? What would happen to these balls? When lines move apart really, really fast, they're going to get really small, right? We got a good answer over here before. The balls get really, really tiny when space is negatively curved. Let's see that. Let's see your vision. Let's turn the dial in the program. Bam. There we go. These are the same collection of balls, but in a negatively curved space. You can see now the balls close to you look really big. The balls far away are about the size of a single pixel on the screen, yeah? But they're actually not very far away in distance. Those balls that are way, way, way look like single pixels, they're 6 feet away. Light spreads out so quickly that they look really tiny. They get microscopic in your vision because light is racing apart and very, very, very few lines of sight hit any ball. It'd be very hard to give this talk in a space of negative curvature. I wouldn't be able to see anyone beyond the third row. You can actually run the math. If I make the radius of curvature -1 with respect to meters, like standard human units, I would need a full-blown telescope to see the back row. How can I figure that out? Well, can compute the angular size. We can do trigonometry for negatively curved space. These functions that show up here are called hyperbolic trig functions. Hyperbolic tangent, hyperbolic sine, instead of tangent and sine. What do we get? Instead of 2r over d, or 2r over sine of d, we get approximately 2r over an exponential. Do you guys know how quick exponential functions grow? When I teach Calc 1, I always try and do demonstration. Oh, there is a board here where we try and draw an e to the x graph, like centimeter by centimeter. Like we draw some graph paper and we take bets on how tall is it going to be 1 meter down the board. Like I draw maybe the first 10 centimeters, so it looks like this. And it turns out that the height is larger than the observable universe if you draw out that far. You really can't draw this graph. It grows really, really, really fast. Yeah, so in here, the units of d are units in which the curvature of space is -1. So you could think about them as if you had, like when you're measuring space, you can measure the curvature, set your unit so that the curvature becomes -1, and then those are the units that can be plugged into exponentials. So it's d over the radius of curvature of your space. Here's the Earth on an Apollo mission in negatively curved space. In actual Apollo, we couldn't see the North and South Pole at the same time. We could almost, but we couldn't quite see them both. In positively curved space, light wrapped around the back of the sphere, and so we could see more than half of the sphere. In negatively curved space, Let's take a look back here. How much of the sphere are we seeing? Just a little tiny, less than half, right? It's kind of a fun math problem to compute how much of the sphere you can see. It turns out to be pi times the curvature of the space squared. So if we measure things in the units I'm using here, you can only see pi square meters. That's why when we look at the Earth, Indonesia can take up almost an entire hemisphere at once, because you're seeing very, very little of the Earth. The horizon is very close in negative curvature. So if you ever wake up on your spaceship and you see Earth and you actually only see the entire hemisphere is just a piece of Africa, you know that space is pretty negatively curved. And that you better land right now, because if you step 6 feet farther away from the Earth, it's going to shrink to a pixel and you'll never find it again. Oops, skipped ahead one. But in negative curvature, there's actually lots of room in this space. Light is spreading out really fast, and that's signaling that there's lots and lots and lots of room for activities. So here, showing how you can stack cubes. In 3D, we know how to stack cubes, like blocks in a room. You stack them in 4 along a side, and then you put a new layer on and a new layer on. In negatively curved space, the number of blocks you can stack grows exponentially as you move out instead of cubically. And so here's what it looks like inside a stack of blocks in negatively curved space. All the little blocks you can see out in the distance are all the same size. They only look small because light is moving apart so quickly that just like your face and just like the Earth, everything looks tiny when it's far away. All right, so that's our warm-up. We've seen positive curvature, zero curvature, negative curvature. But now we want to use those to understand even more. So I want to just show you some quick scenes from slightly more complicated spaces. This next space is a stack of hyperbolic planes. What that means is we have 2 directions in space that are going to be negatively curved, and 1 direction in space that's the stacking direction. This is like the geometry of a stack of Pringle chips. What that means is in those stacking directions, space has no curvature. It's flat. We've just stacked things on top of each other nicely. And in the other 2 directions, it's negatively curved. So here's how you could tell that you were in that world. This is a view from inside of that world. What do we see? In this direction, balls are getting really small really fast. They're shrinking. They're actually getting really skinny too. So what does it mean they're getting small really fast? That means negative curvature. But now let's look as it slowly turns. You can see up there in that direction, the balls are shrinking less fast. Big balls go on for many balls in a row up there. Whereas in this direction, you maybe only see 2 or 3 big balls before they turn really tiny. It means this direction is very negatively curved. They shrink quickly. That direction's not very negatively curved because they don't shrink so fast. You can also build a stack of spheres in space. That would be a space that has positive curvature in 2 directions and is flat in the other direction. And here's how you could tell you're inside there. Here, in this direction, the spheres are getting giant and stretched out into big weird blobs, just like your face filling up the universe. This direction's positively curved. But in that direction and in this direction, wait till it comes back, you see the spheres aren't getting stretched into such weird distorted shapes so much. They look more normal. That's the direction where there's not curvature. That's the direction it looks more like our world. Right up there in the top. Some of the spheres are staying small longer. So if you want to see more of this stuff, all of these animations come from a research project with me and my collaborators. We wrote a technical paper on this. So it's not a good paper to learn this stuff from, but if you want to learn how to make these animations, like how to do the mathematics, it's a paper called Ray-Marching Thurston Geometries. You can look me up and you can find it on archive or on my website if you're interested. But okay, I want to go one more level of weird. We've seen what the world looks like when space is positively curved, negatively curved, and maybe a little positive, a little zero, a little negative, a little zero. But here I want to imagine the world we live on has a bump on it. So here, this is the 2-dimensional picture. So you're an ant living on this world. On this world at the top there, the top of that hill, there's positive curvature. Looks like a hill. Around the waist here, there's negative curvature. You can see it's kind of bending one way and bending the other way. It's kind of like a little Pringle chip along the edges there. That part has negative curvature. So a little bump has a little bit of positive, little bit of negative. And then far away from the bump, it's flat, right? This is like the geometry the Greeks know about. Nice, normal, plane, stuff we've heard of before. Great. So what would it look like if this was the world? Well, we have to compute what the rays of light would do on this world. We have to compute what the geodesics are on this world. And these are the rays of light. Imagine you're standing in the back there where that blue ball is, and these are the rays of light hitting your eye. Of course, it's kind of hard to imagine being a two-dimensional person. So we're going to make a three-dimensional version of this. Here's the 3D version. We can't see the bump because now we're the ant. We're inside the world. But these are what our lines of sight would do. Instead of just having lines of sight move on straight lines like they do in flat space, when they pass through the region of space that has positive curvature, they get drawn back together. When they pass through the region of space with negative curvature, they spread back apart. Does anyone have a prediction for me? What you will see if that white ball is you and you're just turning your head. You're looking away from the bump in space, towards the bump in space, and then away from the bump in space again. This is a hard question, so no worries. Yeah?
Well, when you look right over the bump, there's a focal point, which is to say whatever's at that spot is going to completely fill your vision.
Yeah, you see all the lines of light focusing there? It's a great observation right there. That's like the south pole of the sphere. All of the vision in that direction from these light rays are all pointed right there. Past that, what happens? Think about a focal point on a lens. Yeah?
So if I'm looking at this guy and I'm turning my head, I will see him again briefly. I think, like, if I'm right.
You will see him multiple times. Yeah, you're right. Here. But it'll be flipped. Let's run it. Let's turn on the vision. So here's a live simulation of what I'm doing is I'm ray tracing. Like I'm tracing the rays of light through 3D space, but I'm tracing rays of light not using normal straight lines, but using the lines in this curved space. And this is what you would see. You see a tree over here, right? And then you see the upside down tree here. That focal point that we were noticing, where you see an object kind of everywhere, that's actually this. There's like a single blade of grass that's been smeared out into a ring all the way around there. That's the focal point. It's kind of hard with it moving, so let's stop it and take a look. Yeah, we already noticed this, right? Good job. You guys are great predictors at this point. See, we're getting good at intuition for curved space. You knew the tree was going to be upside down, and the tree's upside down. That's why, because the line of sight leaving the top of your eye after the focal point switches. So the light coming out the top of your eye hits the bottom of the tree and vice versa, past the focal point. But we also pointed out if you looked at your friend, you'd see your friend in multiple places. Well, here I guess my friend's a tree, but we see the tree in multiple places, right? I see the tree. If I look off in the normal direction away from the bump in space, I can just see the tree looking in flat space. And if I look through the bump can bend light in a U-turn, so it whips around and hits the tree in multiple different ways. We actually see the tree 3 times in this image, twice inside the bump and once away from the terrible, horrible, scary bump that I put into the universe. So here's the picture of what's going on there. Here, there's a line of sight going perfectly straight, hitting the tree. And there's also light that's been bent by the bump that comes back and hits the same tree. So this is the location of the tree. And if you trace these back to your eye, you'll see the tree in multiple different directions. Pretty weird. All right. Extra expert level. So this is my favorite space from my research in math. It's called nil geometry. And I can't describe the geometry to you in this talk because I want to talk about other things and it would take a long time. But what I can do is show you what the lines of light are. These are the straight lines in this space. And we're going to try and understand what it looks like in this space. Here you can see right now all the lines of light were spread out. Now they're all collected together in a nice little bundle. And then they're going to get all spread out again. When they collect together, that's positive curvature. When they get all spread out, that's negative curvature. And there's a lot going on here. So I want to focus on just one particular scene. Imagine you're an Apollo astronaut, but instead I sent you to nil geometry. So here's the Earth, and here's your line of sight. You're that white ball looking at the Earth. That's your spaceship. Let's try and imagine what the Earth is going to look like. That white line of sight in the middle, that hits the Earth, right? So that means I see the Earth right in front of me. Right down the middle of my vision, I see the Earth. Those orange lines of sight in my peripheral vision also hit the Earth. Oh gosh, what does that mean? That means I see the Earth in my peripheral vision. But those yellow lines of sight in between the center of my vision and the outside of my vision miss the Earth. Does anyone have a guess as to what that would look like? Yeah.
You're going to see the Earth in your peripherals in the center of your vision, but then there's going to be like a gap that sees, I think, behind the Earth.
Yeah, there's going to be a gap that sees behind the Earth because the yellow light rays go past the Earth. Did you have a suggestion too?
That was basically the same.
Okay, yeah. Yeah.
What if the yellow light? What if when it goes past the Earth, it hits something behind the Earth?
Then you would see that thing behind the Earth in the middle of your vision where you don't see the Earth. It's kind of hard to picture. So again, what should we do? We should stay up late, drink too much coffee, and write computer programs that render it from the inside. So here we go. Here's Apollo astronaut in nil geometry. What we're going to do is we're just going to move away from the Earth. Right now I'm really close to the Earth. Kind of like we did in the positive curvature. I moved away and then my face got scary. The farther away you get, the more the geometry like messes with your brain. So we're going to do the same. Right now I'm near the Earth. It's not scary. But I'm going to start moving away from the Earth. And I'm going to move away at constant speed. No matter what the screen looks like, I'm just going to be moving away at the same speed from the Earth. Don't believe your eyes. Believe me. So, the Earth looks like it's getting bigger. We've seen that before, though. Oh no. Oh wait, do we see the Earth in the middle of our vision and the Earth in the peripheral of our vision? But we don't see the Earth in the in-between? The whole peripheral of our vision sees the Earth. The whole middle of our vision sees the Earth. And in between, the light escapes and goes past the Earth. Let's watch this again to see one more time. Those yellow lines of light skip past the Earth, whereas the orange lines of light form a ring. They are all the way around your vision. And they all hit the Earth. That makes the Earth look like a ring. The Earth isn't changing shape. If you were on the Earth in this weird space, you'd just be hanging out doing Earth people things. The people in the spaceship also aren't changing shape. They're just doing space people things. But the geometry of space between them is causing a mirage. It's causing it to look like this because light has followed curved space. Yeah?
Can your brain adapt to existing in this?
I'm not sure. There's a lot of interesting questions in that direction. So we've put this all into VR and spent a long time in it. But there's a big problem of your two eyes, like right now, like I infer 3D distance from the difference between my eye visions. In this space, it's very common to, through one eye, see the Earth shaped like a ball, and through the other eye, see the Earth shaped like a banana. And your brain just can't assemble them. Or one eye sees the Earth shaped like a ring, and the other eye sees the Earth shaped like a C shape or like a worm. And your brain just literally just superposes them. It can't draw it. So I think it would take a long time for your brain to figure out what's going on. You can't just put a headset on and walk around. It's very confusing.
Wait, so like depending on the height of the curvature, could you see multiple rings?
Absolutely. So unfortunately, I don't have that queued up in here, but if you want to see that after the talk, come find me. When you move away, every time you move 2 pi further away in the units of curvature, a new ring pops off. And so when you're really far away from the Earth, you see lots and lots and lots and lots of concentric rings from farther and farther away light having time to come back and reconverge.
And each of the rings is rotated a certain amount with respect to each other because of the spiral, is that right?
Yeah, that part's a little harder to compute, but yeah, they're all rotated by a bit. Yeah.
So in order for us to perceive something like this, like all the time, would we have to kind of be in a different, like a 4D situation?
No, this is still 3D. It's just curved 3D, and our space is not curved, so we're not used to seeing things like this. But this is just like how, like, I had those surfaces like a bumpy surface. Like if you had a 2-dimensional creature that lived on a curved surface, they'd have a weird life. This is like the curved for 3D. I know it's hard to see. Okay, I'll take a couple more questions and then I'll have to save the rest for the end.
You get a fisheye lens and look through it, you'll see something
Yeah.
resembling this.
That's true. You can use lenses. That's a really good suggestion. So a way to mimic light bending in space is to use a lens. Absolutely. Okay, one more, and then.
Me?
Yeah.
So since it is like since it's in a spiral, if it was close to you, would it be upside down?
Oh, yeah. So the Earth in the middle. Let's go back and watch the Earth blast away. Whoop. Stop. Watch the Earth blast away one more time. So the Earth in the middle is going to be upside down. The ring gets formed, and the light in the middle has had time, just like we saw with the bump. Light goes through a focal point, and then it turns upside down. So in the middle Earth, you're going to see the North Pole on the bottom. This was very weird the first time we saw this in a program. We'd done all the math beforehand to predict exactly what was going to happen, because how else could you debug this? Like if you saw the Earth turn into a ring, you're like, is that a bug or a feature? So we knew the size of the rings. We knew where a ring was going to be in a simpler geometry, not in this one. In this one, we really had to think hard. Great. So that's good. So now we've been through the whole, that was my whole training class on curved space. We now have a little bit of intuition for if you woke up in one of these weird worlds, or if you see a weird picture, we have a sense of, is that due to curvature? Is that due to positive curvature, negative curvature? What are the things that can happen? There can be rings, there can be mirages, there can be multiple images, things can be upside down. That's the sort of thing that signals space is curved. And my favorite thing about math is learning all of this stuff. We did this all just in pure mathematics. Like this came out of just thinking about what is curved space like with no exterior motive. But that lets us ask new questions, questions that could never be asked if you didn't think about these things. A question you could have never asked before is space curved? If you didn't know what curvature was, that was an impossible question to ask, is space curved? Now we know what curvature is. We've seen lots of examples of it. And so we can ask a precise question. How could we tell if space is curved? And is it in the real world or not? It didn't actually take long from the time mathematicians worked out curvature for us to figure out that, yeah, it does matter for the real world. All of this math came in about 1860. And then in 1915 came Einstein's answer. Yeah, space is curved. There's an equation that precisely describes exactly how space is curved. And here's what the equation looks like. I've color-coded the equation for you and put a nice, by John Wheeler, a really nice English gloss of the equation. So the yellow terms here, yellow is geometry, blue is physics. And so the equation says that space tells matter how to move around, and matter tells space how to curve. This side of the equation is about the geometry of space. This side's about matter interacting with the geometry of space. But don't worry, we're not going to solve this equation today. Actually, I was talking to someone in our department today, and they were like, "Steve, I heard you're giving a talk on general relativity at a library. Are you gonna put tensors in everyone's face at 8 p.m.? And I was like, no tensors, don't worry. We're not going to solve the equation. We're going to use all of our explorations to try and understand what we're actually seeing. And the main thing I want to share is, personally, what I think Einstein's greatest insight in this whole picture is. It's that curvature is what we call gravity. That the force we feel, the thing that keeps planets in orbit, the thing that makes my phone hit the floor when I drop it, is geometry. And so here's the picture of why. Imagine you're an ant living on the Earth, and you and your ant friends all decide to walk on a perfectly straight line. You're walking on a perfectly straight line, you don't feel any forces, you're just hanging out, you're walking, you're doing your ant business. And what happens? Those straight lines spread apart for a while, and then they come back together. Any one of those ants walking on one of those paths, like take one of the ones in the middle, just because it's easier to picture. What do they see? They see everything near them getting closer to them as they move forwards. Over time, everything nearby attracts to them. They maybe think, there's this magical force. There's the friendship force. It brings my friends closer to me as I keep walking. My ant friends, they start out, they even try and walk away from me. I've been talking about math for too long, so they're trying to get away. And they can't help themselves. Once they've walked long enough, the friendship force pulls them back together. And they all meet up with me at the South Pole, and I show them tensors until midnight. But then the ants think about it a little more. And our nerd friend Antimedes, walking down the middle there, goes, guys, I don't think the friendship force is real. And the other ants are like, yeah, we know. We don't want to hear any of this ever again. But Antimedes is like, no. What I mean is I think I live on a curved space. And when I move in my curved space, you move in the curved space, we all move in the curved space on straight lines, and space itself conspires to bring those straight lines together. It's not that there's a force drawing you to me. Me and you are both moving on straight lines, and the distance between us is decreasing because space is curved. And the amazing thing is that's what's happening. That's what's happening in the real world. Of course, I'm sweeping a lot of details under the rug here. Most of the curvature is in the time direction. But here's an animation of what's going on. The space, if you draw coordinates on space, like, you know, if I were to, I didn't actually bring anything I could throw, but if I threw something, what do we know? We know since Galileo it moves on a parabola, right? It goes forward and then it goes towards the ground. What's actually happening? It's moving on a straight line through space, but Earth is bending space downwards. The object itself is moving on a perfectly straight line through space, but Earth has bent space the same way that we bent space with my weird dials in our computer programs. The thing you throw just moves on a straight line. It's just the straight lines all hit the Earth, not because of the friendship force or the gravitational force, but by the curvature of space. And the crazy thing is this happens to light too. One of the big implications of Einstein's theory that gravity is curvature is that even light falls. Of course, light's moving very fast, so near the Earth, you don't have time to see it fall. But if you look at a heavy object from far away, it bends light because light's moving on a straight line and space itself is curved. Eddington realized that this was a way in 1919 to test Einstein's theory. Einstein had been telling people about tensors for like 4 years at this point. But nobody was able to make a measurement to tell, is this really happening? Like, this is a way gravity could work. But just like the ants thought that the non-existence of friendship force is weird, people thought the non-existence of gravity was kind of weird. And we need to really test crazy ideas really well. So here's an interesting test. Eddington realized if you look at two stars, from the Earth, we see them in different directions, we could measure the angle between them. If mass curves space, then when the sun gets in the way of one of the stars, the sun will have curved space, and light would bend around the sun. That would change the angle between the two stars you see in the sky. If you looked at them at night, they'd be at a certain angle apart. if you look at them during the day, that angle would have decreased as one of the star's light got refracted by the geometry of the sun. The only problem here is that the experiment requires looking at the stars in the daytime. And that's hard to do, huh? Like, you can do the nighttime part, and then you wait till those stars are in the daytime sky, and then you go take the measurement again, and you go, oh yeah, the sky's blue. Crap. But Eddington realized there was an eclipse coming. And during the eclipse, the moon covers the sun, and the stars come out during the day. And he said, that's when I should do my measurement. I should measure the angle between the stars during the eclipse and see if it's different than in the night sky. And he did, and that is when the rest is history for general relativity. This was the confirmation. I love this newspaper headline. Lights all askew in the heavens, men of science more or less agog over the results of the eclipse. Just so non-committal. They're just more or less, they're excited.
And they ignore the women of science.
Yes, and they ignore the women of science. Absolutely. Yeah, so here's Eddington's photograph of the sun during the eclipse. It's not the best picture of an eclipse I've ever seen, but it was 1919. And they're hard to see here, but there's little marks that he put measuring the position of these stars. So some of those stars are far away from the sun, so their positions wouldn't have changed much in the daytime versus nighttime sky. And others are near the sun. And so Einstein's theory predicts exactly how much each of those stars should have moved in the sky. And so he compared this picture and these circles to the nighttime picture and verified that matches relativity theory. I think that's really incredible. But what's even more amazing is these days we have better cameras and we can see this sort of thing. We don't have to wait for an eclipse and measure a couple degrees of angle between the stars. We can just take a big telescope like the James Webb and point it at the sky. And we get pictures like this. What always blows my mind is we luckily live in a world where Einstein lived a century before this telescope and explained what we were going to see. Think how weird it would have been if nobody knew that space could curve. And then we built a telescope, and all the pictures came back looking warped, like that, or like that, or like that. And we were like, what's wrong? Nothing's wrong. Our theory of physics would have been wrong. But we live in a very, very fortunate world where we understood all of this before we ever built a telescope that could do it. We understood it all through mathematics. But what's going on in this picture? We see something in the middle there, and we see a ring. We've seen rings before, right? We saw rings in our math world. What do rings mean? We see a ring when light starts heading away and comes back together. This is where we saw a ring, right? In my favorite world, in nil world. That's where the rings came from. Well, here's a simulation. This is solving Einstein's equation now, instead of solving those other geometries. This is the actual physical geometry of the universe type equation. And here's the rays of light. Simulating there's a heavy mass here, and here's light going past it. What happens? They all bend in and hit each other. That's why we see rings. So having understood it mathematically, we can predict what the solutions of Einstein's equation are gonna look like. We know just from looking at James Webb pictures, like I see this picture and I say, oh, I know what's happening. Light rays are moving apart and they're coming back together. They're focusing, they're making a ring. And then I go home and I do tensor, 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 tensor. And then I figure out, oh, what was happening? The light rays were moving apart and they were coming back together to make a ring. Look at this thing. This picture would have really confused me. In particular, those three things are the same galaxy. This picture here, those are the same galaxy, but we're seeing them twice. This here, those are the same quasar. We're seeing them 4 times. This would have been the absolute most confusing thing to me if we didn't have a mathematical theory and we built a telescope and I saw the exact same galaxy twice. It'd be like, what are the chances? And then I looked at the next galaxy and I saw 4 of it. I'd say, I think I don't understand what the chances are. This is wild. But we know what's happening, right? This is just multiple images. This is like our bump world. Some of the light's going through space that's not curved too much, and others getting U-turned by curved space. And so we can simulate that too. Once we know what's going on, we can do tensor, 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 and plug in a big mass. And look here, whatever object is at this location in space, you see in 3 different directions from your eye. If you had a telescope here, it would look in this direction, and this direction, and space itself would bend all of the light to show you the same galaxy 3 times. All right, now we've really done enough. We're here for the finale. We can now look at a black hole. We've seen curved space, we've seen curved space-time. And now I want to talk you through a little bit, what is this idea of a black hole? Like, this is one of those things in physics that I heard about way before I knew anything about it. Like, it was one of those like really cool words, but I didn't know what it meant. So here's a way to picture it. Black holes were actually predicted long before we understood curved space. They're actually predicted relatively quickly after Newton by this idea. Newton realized that, well, when you throw something, it hits the ground. Newton didn't realize that. People knew that. People have thrown things before. But what Newton realized is if you throw something fast enough, it goes into orbit. That the same force that draws something back to the Earth is the force that causes orbits, universal gravitation. And Newton figured out with his invention of calculus, you could compute all these things. And you could figure out what speed you need to go to get into orbit and what speed you need to go to escape the Earth altogether. It turns out if you go 11 miles a second, you can get off the Earth. You can go away from the Earth forever. It's called the escape velocity. If you go slower than that, you get trapped in orbit or you fall back down. Newton worked out the equation for this, and he found that on the sun, you have to go faster. Most things you try and throw on the sun fall back into the sun because the sun's heavy and there's a lot of gravity. You have to go really fast, 300 kilometers a second to get away from the sun. About 100 years later, John Mitchell said, guys, what if there's a really big star out there? Like, we only see stars of certain sizes, but what if there's a star so much bigger than we've ever seen? And his colleague said, well, then we would have seen it. Like, if it was bigger than the things we see, it would be there. And he goes, no, we wouldn't have. That's what worries me. Watch this. If the star's so big that the escape velocity to leave the star is greater than the speed of light, light itself could not get off the star. How do I see stars? I see stars by light coming from the star to my eye. If a star was so big that its escape velocity was bigger than light, that star would not shine. That star would be dark. He called them dark stars. It turns out Newtonian physics is not the correct theory of the world, but this idea carries on. What if you put enough mass somewhere? The new version would be, could space be so curved that light could not escape? So here's a downward view of some sort of a spirally tube like that. This is us trying to guess, like, what would it mean for space to be so curved that light gets stuck? Here, there's a ring in this tube where as soon as the light falls into that hole, it gets stuck doing like a barber pole spiral down the hole forever. There's a region of no return. Once you pass that region, the light never comes back out. Anything inside that region you can't see. The actual math of this was worked out not too long after Einstein first solved his equations by Karl Schwarzschild. And this is the Schwarzschild metric for space-time. This is a solution that just accurately describes this sort of ultra-curved space solution. And so here is the picture from the beginning. What we see is, again, now we're in the 3D version. So space is curved, but we're in the space, so it's weird to see. These lines, these are rays of light. You are at the very top of the picture there. You're that little ball, and you're looking down towards the black hole. What happens is there's a clear ball right here. This is called the photon sphere. This is the point where as soon as light crosses this is like the mouth of that big tube that I drew. Once light gets inside of there, it's stuck forever. The black ball in the inside is where you're really stuck. If you get inside the black sphere, that's called the event horizon, you can actually never come back out. The clear sphere, if you got inside the clear sphere and you realized you were in there, you could like turn on your rocket engines and work really hard and get away. But if you didn't turn on your rockets, you'd be doomed. Inside the black sphere, you can never get out. That's like deep, deep in that hole. And these are all predictions of the equation. The equation was actually written down long before people understood the consequences. It took us a long time of thinking about curved space to understand what the equation was saying. But here's a picture. So here's a simulation of a black hole. In the middle there, you see a black circle. That's the photon sphere. That's where once light goes in there, it's gone. That's the dark star. No matter what's in there, you'll never see it because light's never coming back out. What's going on here? This is a simulation of a binary black hole. This is Cygnus 11. So there's a star in orbit around the black hole, which is this bright ball we're watching. We'll watch it go by one more time here. And try and understand what's going on. It's going to come back. What do we see? We see multiple copies of the star, right? See the star over here? See the star over here? And then the stars form a ring. So we're seeing all the sort of behavior that we're kind of used to. Black holes aren't that different from any of the other things we've seen. They're the first example people hear about, but black holes are just curved space, just like the other curved spaces we've seen. You get multiple images, you get rings. Let me see. It's stopping. Oh yeah, here we go. This one, I thought this was an animation, it's not. Where did we see multiple images and rings before? It was with the bump world, right? With our bump universe. What was the other thing we noticed in bump world? Not only did we get rings and multiple images, but once you got past the focal point, things were upside down, right? So that tells us a prediction about what black holes should look like. If, don't do this experiment at home, but if there was a black hole between you and your friend, and you tried to look at your friend, what would you see? Well, part of your friend might look like a big ring shape, and part of your friend is going to look upside down. I didn't have a picture of your friend, but I do have a picture of San Francisco. So here's a black hole in San Francisco. Don't do this at home either. What do we see? We see the dock here, and then we also see the dock upside down near the black hole.
So what's going on here is the image, the dock is behind it.
Yeah, the part that we're seeing.
The light around the black hole for you to see.
Yeah, exactly. So we've seen examples of spaces where light gets bent and passes itself and focuses. But black holes really are an extreme example of this. I want to show you one cool picture of just how tightly wrapped light can get in the curvature near a black hole. Here the light doesn't quite fall into the black hole, but it gets slingshot back at you. So when you look at the black hole, not only do you see what's behind it upside down, you also see yourself. Black holes act like mirrors. If you look close enough to the black hole, light can do a 360, a 180, come around and come right back at you. I'm getting ahead of myself because, of course, light can also do a 360. That light orbited around the black hole several times before escaping. The closer and closer you get to the black hole, the more times light can wrap around like a barber pole before escaping. So what does that mean? That means if you're looking at a black hole, you should see what's behind the black hole. Obviously, you always see what's behind something in normal life. But you should also see it kind of upside down in a weird way because of the curvature. But then you should see yourself because some of the light's been reflected back at you. But then some of that light got turned back around again, and you should see the background again. And you should see yourself again, the background again, self again, the background again. Black hole kind of works like a mirror, like two mirrors. And it's kind of hard to draw a good picture of this. So what I did was I put a black hole in a very boring space, a space that the whole walls of this world are tiled with grids. The grid behind the black hole is white, and the grid behind me is red. And so here you see this is all light that went past the black hole. Near the black hole, this red light that's light that's slingshotted around the black hole and come back at me. This would be a picture of me if I were here. This is a picture of what's behind the black hole, and this is me. But looking closer, beyond that red, there's another stripe of white. That's light that's done 2 orbits, and now we're seeing what's behind again. If you zoomed in farther, there's infinitely many of these stripes, but they shrink really fast. All right. So those are some pictures of black holes, but this is probably, if you've seen a picture of a black hole in the last like 5 years, this is probably the picture of a black hole you've seen, yeah? The like bright, weird donut thing from Interstellar. So what I want to end with is us understanding this. Why does a black hole with a disk of stuff around it look like that? So let's simulate it. Let's think about what light does. What is that disk? That disk is a disk of like gas and dust falling into the black hole. There's my black hole in the middle. Here's me. What we're going to do is we're going to simulate light coming from me to the black hole. But what I want you to predict first, why do I see the disk on the top and on the bottom? Why do I see it above the black hole and below the black hole? What's going on? Does anyone have a guess for me? I'm seeing a lot of the right hand motions. A lot of people going, "Ooh, yeah."
Maybe since maybe when it goes around, never mind.
No worries. It's hard. It's general relativity. So let's just run the simulation. What happens? Light moving towards a black hole. We've seen what it does. It goes away and it comes back down. So what do you see if you look over the top of the black hole? Light gets bent by the black hole downward and it hits the disk behind the black hole. So if you look up, you'll see the disk behind the black hole. But what if you look down? If you look down, light gets bent up. You see the bottom of the disk behind the black hole. That's what we're seeing here. This is the front of that white disk. This is the bottom of the back of the disk. And the top is the top of the back of the disk. Those are just light going around the black hole and hitting the disk in the back, focusing in on there. And then finally, we have pictures of these disks now. With the Event Horizon Telescope, here is the black hole's disk in the middle of M87. And here's the black hole in the middle of our galaxy. Oh, thank you. Need some water. The light's coming to us, correct. Light's coming to us. But it's easier to picture what you're seeing if you think about it backwards. Yeah, physically light is coming from the world.
I can never wrap my head around the universe because I always think that it should be contained in something. Is that because I think in Euclidean geometry and not this way? Yeah. So exactly. Like if we think about ants living on the surface of the plane, like if they were first trying to imagine a universe, they might draw a big circle in the plane and say the inside of the circle is the universe. Like that's all the space that I know about. And then it's very natural for the ants to say, well, what's outside the circle? And in the plane, there is an outside to the circle, so that's a meaningful question. But then we find some of these other ants that live on the surface of a sphere. That sphere is finite in size. It has a finite surface area, but it has no edge. There's no boundary circle or anything on the outside. So those ants, even if they live there, they're picturing two-dimensional. They're still thinking like the plane. It turns out if they go explore their universe, they'll never hit an edge. And it's because their universe is curved. So to Einstein's equations, there's solutions to Einstein's equations that are infinite universes that are flat like ours. There's also finite universes, things that have a finite total volume but have no edges. There aren't any solutions with edges. So the universe, from the perspective of general relativity, doesn't have an edge to it in space, but it might be finite in size, like a sphere.
was just wondering, so, correct me if I'm wrong, but so, it's the curvature of light bending, it's not exactly, so gravity is not the cause of it, gravity is the effect of the curvature, and if I'm correct, the planets can cause curvature in reality, but why is that?
Yeah, so gravity is another word for curvature. Like, we didn't know that when we came up with gravity, but now we know gravity and curvature are the same thing. So if we say that light bends because of curvature, or light bends because of gravity, those are the same thing. One's like thinking like a geometer, like thinking like a math person, and one's like thinking like a physics person. But they're the same thing. That's Einstein's big discovery, that they seem different, but they're the same. Yeah, they're curvature, or mass determines curvature / curvature determines mass. Yeah, there's an equation relating the two.
So like, just forget from a physics perspective, right? Because gravity, like it acts at the speed of light. So how would that work in the geometric sense then, right? Like.
Yeah, so that is a great question, which fits into the top of the mound that I swept under the rug for this talk. So all of the things that we've been able to see pictures of in this talk are all solutions that are called stationary and static, which are they're very symmetric solutions, which allow me to ignore the time direction for all of these and be correct. For anything that's not like super nice and symmetric like this, that scary Einstein's equation I put down at the bottom, that's actually a wave equation. It has gravitational wave solutions to it. All the solutions we've been looking at have no waves in it. So here, the gravity is like, it's like on a drum surface. You could have waves on the surface of a drum, but you could also have the drum just like relaxed in like a stationary state. Like you could put a heavy mass on something and it bends down and eventually it stops wiggling. These solutions have all been of that type, but there are wave solutions as well. Yes, absolutely.
Have you done remarching in a time-dependent geometry?
Yes. So let me think. In these black holes at least, I've remarched on the mass parameter. So you can have a dial to change the mass of the black hole. And in some other geometries that are only more like interesting for geometric topology research, there's some parameters in there that I'm interested in, particularly that nil geometry I was mentioning. There's a one parameter family of geometries between that and Euclidean space where I've remarched the interpolation between the two. So trying to see slices of that four manifold.
So going back to your question, like if you have two black holes colliding, that's a huge gravitational event that sends out gravity waves. Those gravity waves travel at the speed of light. So I wasn't sure if that was part of your question or not, but.
So we know what looking at a black hole is like, but do we know what it is like when we're inside a black hole?
Ooh, well, we know if general relativity is true, we know what will happen. We can do the math. What we don't know is we don't have any experimental test that confirms that general relativity remains true inside the black hole. Because if you went in there and you checked, you couldn't tell me on the outside. But if we believe general relativity, like if we just follow the mathematics, we can calculate exactly what happens on the inside. Yeah.
So to your question, so one of the things that happens with general relativity is time dilation. So if you've got somebody falling into a black hole, we would see them fall in. But in their time frame, as they get closer and closer to the event horizon, time takes infinitely long. So in their own time frame, they would never enter the black hole. It would take them forever. So if we believe general relativity, and it just the fact that space-time gets warped and the time part gets stretched out for them, so they would never see themselves.
That's what the people on the outside would see. The infalling observer actually gets into the black hole. They get in no problem. But people on the outside never see them enter. Yeah, it is confusing. It's like two different observers disagree on what happens, which is really weird. Like, person on the outside they actually never see any matter, even the infalling star, ever get into the black hole. They see it all slow down. But someone falling in, they just zip right past it. They don't notice any of that. There's a big paradox related to this called the black hole information paradox and black hole complementarity, trying to understand what's really going on here. But yeah,
Black holes are weird.
Okay. Well, thank you, Dr. Trettel.
Yeah, thank you.